a very brief intro. So our next session is Communications and Autonomy. Our moderator today is Dr. Thomas Kashingaki. Dr. Kashingaki is a systems director in the Civil Space Program Operations Division in the Civil Systems Group at the Aerospace Corporation. He has served in this position since 2014, where he leads the implementation of space asset protection for NASA and other civil agency missions. And he also manages research in the role of intelligent systems in space traffic management and conjunction avoidance risk assessment activities. So I think he's all set. Excellent. Take it away. Thank you.
Good morning. Are we awake yet? Good. It's hard to follow that presentation. That is an amazing accomplishment. Hopefully it'll go up. And in fact, one of those slides showed everything we're going to talk about today, which is advanced communications and autonomy for space exploration. So again, it's great to be in Cleveland. I thought I was going to be the first person to say this, but apparently everybody in this room had an internship at Lewis or Glenn. So I'll just add to the bandwagon. Mine was in '87, I believe. So let's see. So I have a great panel here. And what we're going to try and do is give you a compelling look at the future of autonomy in space and the need for intelligent and cognitive communication required to make autonomy sustainable and reliable and safe. Aerospace agencies and companies employ very complex systems of systems comprised of hardware, software, networks, and human-machine interfaces, with an increasing use of intelligent agents, artificial intelligence, and machine learning. These systems are evolving as intelligent ecosystems to operate autonomously, including the capacity to routinely, and this is important, upgrade themselves without human intervention. So there's a lot of things going on. We have a great panel. Everyone up here is an expert in their field. Actually, really pleased to have every one of them. What I'm going to do is I'm going to give a brief introduction before each of them speak. They'll give a brief presentation, and then we'll do, I have some leading questions, but I'm hoping that while we're talking, you guys will come up with some more intelligent questions, some prying questions, some questions that will make us all scratch our heads and wonder whether or not we want some of these cognitive artificial intelligence machines to be out there. And I think we'll have a good time. We really want it to be interactive, so please participate. So the first speaker, and I'll start at the other end and we'll work our way back to me, is Badri Yunus. He's the Deputy Associate Administrator for Space Communications and Navigation, otherwise known as SCAN. And he's responsible for all of NASA's space communications and navigation infrastructure, as well as data standards and spectrum. And I'm sure he's going to speak a lot about spectrum. He manages the SCAN programs at NASA that include the Deep Space Network, the Space Network, the Near Earth Network. And he's also responsible for the development of enabling technology and capabilities critical to meeting the agency's vision for an integrated SCAN architecture. And I'll let you know that I work on doing some interesting things with the SCAN network and networks, including the Space Network and the SGSS. And over this summer, we're going to be doing some very interesting red and blue exercises for SGSS that have never been done in the network before. So anyway, I turn it over to Badri and take it away.
Thank you, Tom, and good morning, everyone. So great to be with you. The earlier clip we saw with the administrator talking about going to the moon, and that we are going. We are definitely going. We are going to do it in a way we haven't done it before, partnering with other space agencies, partnering with the commercial sector. There are plenty of commercial opportunities that space offer, and we would like to sensitize the commercial sector about the need to invest in space. And we don't need to go as far as the moon to do this investment. The near-Earth environment definitely is going to get so crowded We are looking at a number of commercial systems being deployed to provide the kind of internet in space. You all heard about the OneWeb, the SpaceX effort, the Amazon. Everyone wants to invest up in space to build the communication networks of the future. At the same time, we are talking about government entities deploying new system up in space, but the power of the commercial sector is by far much stronger and larger than that of any government agency or the entire US government. So we are going to see a lot of systems up there, and NASA would like to take full, advantage of these systems. NASA would like to move away from building its own unique capability in space to depend more on commercially provided services. And in order to do that, we need to work together. NASA will need some certainty and predictability in the kind of support it can get. Up in space, it's a different environment. Most of these networks have so far catered to suborbital and ground and surface kind of users. Up in space is a little bit different. The environment, from radiation to the dynamic aspect of space, makes it a little bit more challenging. So there will be plenty of system, and in order for NASA to get the assured access, NASA will need to have the ability to use any of these systems up there. So interoperability is so critical for our future operation. And interoperability requires a lot of things. Interoperability requires some changes to the way we think, the corporate America think. And the interoperability requires a new technology. Much of the technology has been evolving over the past 20 to 30 years, but we are about 10 to 20 years behind finding the application of this technology. We are talking about cognitive technology. I remember as far back as the 1985 when we were trying to build neural networks, but we were limited because we didn't have the processing capability and the number crunching capability to implement it back then. We've gone a long way. In addition to that, because of the dynamic aspect of space, we'll need to rely on good PNT capability, positioning, navigation, and timing. We need to be able to have quick maneuver recovery. We need to be able to have the kind of autonomous operation. And for that, we really need to work on the kind of PNT receivers that can support and sustain this autonomous operation. Again, all of these guys operate at different frequencies. They have different waveforms. So we need to rely on the kind of capabilities that will allow our users to adapt to their signals from a waveform, from a frequency perspective. And we need to overcome the regulatory burden. You all know we have a bifurcated process in the United States. We have the State Department doing the international regulation and representing the US internationally and regulating the utilization of spectrum. Nationally, we have the FCC and NTIA, and they are always at odds, fighting among themselves to regulate the utilization of spectrum, government, non-government, commercial, near Earth, deep space. It's kind of, makes you kind of wonder about, an alternative to this approach. And we are working with both entities and with the administration to propose something for space, and a good regulatory regime. And we need the kind of technology that will allow us to ride on all of these regulations, transparent to any regulatory regime. So SCAN has been working with all of our performance center to enable that. We have taken the PNT capabilities that are meant to the ground, looking at all of the GNSS systems that have been implemented or in the implementation stage, the global one as well as the regional one, and try to extend the reach to beyond the surface of the Earth. We are talking about the space service volume that will take us all the way to geosynchronous orbit and all the way to the moon. We are actually working on PNT receivers that can get navigation solution around the moon, and hopefully we'll have it in time to enable the lunar exploration. We are looking at the PNT capability because, as I said, there are a number of things that PNT can provide you, which is a good situational awareness from positioning and also from a position perspective. If you need autonomy, you need the machine to know where it is, and you need to reduce the contact with this machine. It's going to be extremely dynamic, and as the space gets so congested, it's going to be a nightmare to put a person in the loop trying to manage all of these things. We have the technology. We need to implement this technology to allow for this autonomous operation and to the independence from the time and the inefficient human aspect. We are talking about this cape, and we have reached many agreements with the Air Force that will allow us to make full utilization of GPS to all the way to geosynchronous. And we are working on multi-GNSS receiver. As you go up in space, the number of spacecraft that you can see to derive your navigation solution from gets smaller and smaller because you are looking at the GNSS satellite from around the limb of the Earth. So you need more than just one GNSS system. We are working to take advantage of Galileo and also GLONASS, as well as some of the regional global regional navigation systems. This is in the work, and so far we are having a lot of success. Cognitive technology, we've talked about it. Again, when you are up in space in a highly dynamic environment, getting a human being into the loop will take time. It's very inefficient. May not be able to respond in real time to changes and to traffic conditions across all of the channels. So we have been investing very heavily, and I believe Don will be talking a little bit about that in this technology. But we are going to take it beyond the Earth. We are exploring an option to implement this capability on a network of small satellites around the moon to provide this capability to enable proper communication with users on the surface of the moon together with the gateway. As you all know, the activity around the moon will center on the South Pole. We don't have direct line of sight. We'll need some capability to relay the data between the user and ground activity with the mothership, with the gateway, and back to Earth. This is it's a notional concept, but we are working on it to provide not only the reconfiguration and of the system to talk to many systems, but also the robustness and the 24/7 support of ground level activity. I talked about riding over the regulatory constraints. We are working on wideband receivers that can operate through much larger bandwidths. So I'm talking about the entire Ka band, a single receiver that will allow our user to roam in space, selecting and tuning its frequency to the frequency of a particular provider, and be able to change, reconfigure itself, definitely in conjunction with the cognitive radio, because the smart has to reside over there, and the automatic routing, updating the routing table based on the conditions of the various channels has to be provided to this receiver to be able to reconfigure. And so we are looking at a very, the kind of capabilities that will allow our users to roam in space. And we have a number of activities, in particular here at Glenn, to develop this receiver for the future. We are looking also at optical comm. Optical comm is not regulated. The regulated spectrum goes all the way to 280 gigahertz. Anything beyond is not regulated. It's common. It can be shared among near Earth, deep space, for government, non-government, national, international users. What we need to work on is the compatibility in the technology and the standards. We have been working very hard within CCSDS to ensure we have the proper standards. We have a number of activities that are going on, will be demonstrated in the next year or two, related to near Earth and related also to the human exploration in particular. We have a payload that will be going on the space station called Illuma that will be communicating with that data relay satellite, the LCRD. And we are looking at the same technology to be used on the gateway and in particular the PPE. And hopefully we can enable our users up in space to transmit data well beyond the 1 gigahertz. We know the requirements will be evolving to reach potentially the 5 to 6 gigahertz, gigabit per second. And you cannot close that link with the existing RF systems. It will be a burden on the gateway. So we are looking at good size payload to probably be on the gateway by 2028, but we need to start with some capability in the 24 timeframe. At the same time, we are looking at deep space, and we have a payload that's flying on the Psyche mission. It will be launching in about 3 years, and will be going to the asteroid Psyche. At the same time, using an optical link. At the same time, we are converting our 34-meter antennas, looking at the inner aperture of the antenna to provide a telescope capability. Building a telescope of this size will cost about $100 to $150 million. Retrofitting existing antennas to just take the inner aperture and put mirror quality panels over there cost us less than $20 million per antenna. And over time, as the population of optical users start to escalate in the future, we'll be doing the same thing with all of our antennas, and we have about 15 of them by the time we reach maximum capacity. So the future looks good. We are talking about the kind of technology, the kind of policy, the kind of processes that will take us to an environment where we can have full autonomy in a highly dynamic environment. That's all the time. Probably I exceeded my time, allocated time. Thank you all.
Very interesting, thank you. Our next speaker is Dr. Melih Mousavi. Nelly is a senior professional staff and Van Allen Probe project manager, which is coming to an end this summer. Great mission at Johns Hopkins University Applied Physics Lab. She's also the co-founder of the Institute of Trusted Space Systems, a joint institute between APL and UMBC, University of Maryland, Baltimore County. I should have taken a breath. Dr. Mousavi is an assistant research professor in the Department of Electrical and Computer Engineering in the Whiting School of Engineering at Hopkins, and an adjunct professor at UMBC. She received a BS degree in electrical engineering from Oakland University, Michigan, and an MS in electrical from Johns Hopkins, and a PhD in electrical engineering from the University of Maryland, Baltimore County. And she's going to talk to us about the advances at APL and where they're going in the future. So thank you.
Thank you so much for having me here today. This is very exciting. So in my short presentation, I want to focus a little bit where we were in the last 20 years with bringing the autonomy in a space domain at APL, and where is our vision and where do we want to go. So the future of a space system has changed dramatically the last couple years, and we see that there is a revolutionary transformation in the number of the spacecraft that exist. And there are two fundamental changes. One, we're looking at global connection to satellite constellations, and in order to do that, you really need to have eliminate or lower the human intervention, and it needs to be more autonomous. So from the last 20 years, we've started to look at how we can bring autonomy to a space domain. And I can really categorize the progress in 3 different levels. From 1996, the nearest spacecraft was the first one that was more localized level of autonomy. And then we had the ACES spacecraft, Time, and Contour. So these 4 missions, as I mentioned, they were more localized level autonomy systems. And they increased the, can you hear me well when I, okay. We increased the functionality and, and responsibility of autonomy very localized. Then the last 3, the next 3 were more varied systematic approach with Messenger, New Horizons, which is still in operations, and Stereo that is still in operations. They were more varied systematic approach. And the last 2, the Van Allen probe mission and Parker Solar probe, that were more formal, consistent system level, that were integrated in the systems. For example, there were a lot of autonomy systems in Van Allen probe, but the more heavy side was on the ground. So those decisions were making by a spacecraft, but the ground station was responsible for putting it, implementing it. But for Parker Solar Probe that we successfully launched last summer, it was more advanced because there are periods of time that we are on the other side of the sun and we have no access to a spacecraft. So the spacecraft, it's much more intelligent. And of course, our newest mission that we are very excited about is our Dragonfly. So Dragonfly will have a different way of how we're looking at autonomy system on this spacecraft because we are very bandwidth limited and we want to send a lot of high data and a lot of good science data. So we need to make sure that the spacecraft is capable of analyzing and having a lot of onboard autonomous systems. So in order to summarize, as I mentioned, if you look at, for example, ACE had like 64 rules, NEAR had 165 rules, and Messenger approximately was 3.5 more complex than Contour. So I'm just very excited to, in next couple years, to talk about how much more Dragonfly is going to be more complex than how we started this journey. So, but really, these are all about single spacecraft and one single missions. And our goal is to look at how we do a constellation of satellites because that's where it really gets complex. And we think the solution is really to look at the getting the bio-inspirations. From 50s, we've been inspired by, species and how they do the communication model formations, their group size. And we have great mathematical models, and we want to bring those to space domain. In the last 10 years, we've done a good job to bring those on drones. And the next step to bring those capabilities to space domain. And at APL, we have a very interesting sector that has the Intelligent System Center that it's looking at all these things in terrestrials. And our goal is to bring all those capabilities that exist in a space domain. So when we're talking about the constellation of satellites, again, it's very complex and you have a limited time to talk to your spacecraft. So it's very important to have a data capturing, scheduling, onboard planning that can all be done inside the spacecraft, and the networks and the planning. And also we need to do a better job in bringing AI to the ground station. So those are the 3 different areas that we are very focusing to bring the AI to the space domain. And really, when we talk about cognitive, there are 3 different spectrums. We want to make sure that they are adaptive, and they are cognitive, and they are intelligent. So I just want to mention that we've started, the last missions that we had, the Parker Solar Probe, we were very proud of the amount of the AI that we brought to the spacecraft. Our next goal is to bring those capabilities to interstellar missions. And the future, it's very bright in AI. I think in the last 5 years, we've done a great progress. And if we just continue doing this, it will be just great.
Nellie, appreciate it. So there's the beginning of the cognitive. Now we're going to hear about another approach to AI and intelligent communication. So Dawn Emerson is the Chief of Communications and Intelligent Systems Division at Glenn. She's responsible for leading and managing all research and development of advanced communications and intelligent systems for application in current and future aeronautics and spaceflight systems. She began her NASA career at Glenn in a year. We don't care when.
Gee, thank you.
After 6 years of private industry experience as a research and development engineer at Motorola, where she was responsible for the development of radar and communication systems. Prior to her current position, she served as the NASA Engineering and Safety Center, the NESC, chief engineer at Glenn. She earned a Bachelor of Science degree in electrical engineer from, it's hard to say this, the Ohio State University. Sorry, I'm a Michigan man. I'm sorry. But she's really good, so, and she has a Master of Science degree in electrical engineering from the University of Toledo. She's going to talk about NASA's Cognitive Communications Research Program at Glenn, and this should be an interesting add-on to what Nellie said with a different twist. So thank you.
Very good. Well, with that introduction, so what I wanted to do this morning is just talk very briefly about some of our accomplishments in communications in the past, and then how that has really paved the way for our current work in developing cognitive technologies and autonomous communication systems. So going back in time here a little bit, we've partnered with industry all the way back into the 1970s to pioneer the advancement of traveling wave tube amplifiers. Now, this technology significantly increased the signal power of satellites, and really ultimately kind of gave rise to the large number of satellite television channels that we have today, you know, among other things. And this technology has also been used extensively in a lot of NASA missions. So then moving on to the 80s and 90s, did a lot of research here in communication technologies that were ultimately demonstrated on the Advanced Communications satellite. Some of these technologies include onboard processing and really the effective use of the Ka-band spectrum. And so this higher frequency has much more capacity and really has had a profound impact on the satellite communication industry. So a little bit more recently here, we developed the Space Communication and Navigation testbed, and really to promote the use of software-defined radios in space applications. So software-defined radios, for those of you who may not know, are really transceivers, but they have a large portion of their communications functionality implemented in software. So what this enables are the systems to be reconfigured and provides much more flexibility in our systems. So the SCAN testbed contained 3 software-defined radios, and it operated on the International Space Station for about 7 years. And it was really a platform that allowed us to do a lot of advanced demonstrations in communication, navigation, and networking techniques. During that time, we reconfigured the radios, I think 888 times. So like I say, this really was something that helped. It was a proving ground for our cognitive communications program that we have today, and really paved the way for a lot of the technology development that we're doing. So today, here at Glenn, we're continuing to innovate and develop advanced technologies to revolutionize future communication architectures for both space and aeronautics. One of our key goals here is to infuse cognitive technologies into these systems. We really feel that this will help, improve the performance, reliability, resilience of these systems, along with reducing the operational burden and user burden of these systems. So, when I'm talking about cognitive communication systems, what I'm really talking about here are systems that understand or have knowledge of their current operational state, but also have situational awareness of the environment around them. They're able to, and how that environment is changing. They're able to analyze that environment, predict, and then reconfigure and adapt in order to optimize performance or meet stated objectives. And these systems also have the ability to learn. So in developing these systems here at Glenn, we're really tapping into a number of our core communications disciplines to develop integrated systems. So again, some of these discipline areas include signal processing and machine learning, our advanced RF technologies, network research, quantum communications, and system architectures. And I just wanted to mention, too, when we're talking about infusing these technologies into our systems, we're really looking at all levels of a communication system. So from node to node, but also across entire networks, having intelligent routing across networks, and then throughout systems and system of systems. And I'll give you a couple examples of what I'm talking about here. So my first example is an example of how we've optimized node-to-node communications. And this is showing some experiments that we did on scan testbed. So in this case, we've autonomously reconfigured the software-defined radio, its parameters, and some of those parameters could be their modulation, its coding, its power. So those parameters were reconfigured to compensate for a dynamic link environment. So the link environment could be changing to things because of like obstructions, weather, RF interference. We did a series of these experiments on scan testbed, showed that we could reconfigure in real time, and we really showed how this was able to increase our data throughput. My second example here is an example on intelligent routing, and this just kind of simplistically shows how we've autonomously selected the best link to optimize performance, and here we are looking at things like data rate and latency. And the third example kind of demonstrates something that we refer to as user-initiated services. So what we're talking about here is if you look now, the way scheduling is done on the space network, if you want to schedule those services, it typically takes about 3 weeks. You have to do that 3 weeks in advance. So with this capability, the spacecraft is able to request services, and we were able to show how through autonomous scheduling, we were able to reduce the lead time from that 3 weeks to 15 minutes. So moving into the future here, kind of look at just some graphic pictures of what our architectures might look like for both aeronautics and space. And you see the future of these architectures are quite complex. If you look at aeronautics, I think we've heard over the last couple of days, urban air mobility. So the introduction of these new entrant vehicles into the airspace is going to cause some dramatic changes. We're really going to need reliable communication, navigation, surveillance systems for safe integration of these vehicles into the airspace. As Badri was just talking about here, our future space networks, complex with the integration of commercial service providers and all the new assets that we're going to need for Moon and for Mars. In both space and aeronautics, these systems, there's a long list of desired attributes. And really, if you look at both space and aeronautics, a lot of those attributes are very similar. We talked about the need for interoperability, autonomy. We need these networks to be very reliable and also be able to evolve over time. So we're really looking at some of our cognitive technologies to really help us meet some of those challenges. And so my last chart here, looking at our program as a whole in cognitive technologies, we're really looking to merge machine learning with our aerospace communication systems. And I talked about a number of the areas that we're working in here in cognitive communication. This gives a little bit more of a holistic view of some of the areas that we're looking at. One of the things that I'll just mention that we hadn't talked about too much, but follows on to some of the things that Badri was saying is with the integration of commercial service providers, interoperability is really going to be key. So if you look at a couple of these things that I hadn't really talked too much about, modulation, recognition, and seamless networking and connectivity and handoffs, those are going to be really important. So those are areas that we're looking at moving forward. So thank you.
There's a lot of room for those prying questions I asked for, so start thinking, because especially...
Keep them easy.
No, especially the stuff about security and anomaly detection, and those are some important parts. So before we move to Tim, I just want to mention I stumbled across a very interesting article on LinkedIn today that talks about how the space network was absolutely necessary for the lunar landing. And if you want, just search on space network and lunar landing. It's a very short but very concise story, which brings me to a little anecdote before I introduce Tim. Is 50 years ago, I was 4.5 years old. So you do the math, you can figure out how old I am. But I live a little boy living in Nairobi, Kenya, and the lunar landing was going on, and we had no TV in the house. So for some reason, my dad was inspired to go out and rent black and white TV about this big and bring it in, and we watched the lunar landing all around the TV. And it just occurred to me this morning that was probably the first time I realized how important communication is to the space program. And here I am 50 years later. So, all right, moving on, away from me. Tim Deaver is the director, newly minted, not too long ago, as the Director of U.S. Space Systems at Airbus Defense and Space, responsible for managing all of the U.S. government space-related marketing, program capture, et cetera, for Airbus Defense and Space. Prior to joining Airbus, he worked for SES in the SES Government Solutions for over 10 years, where he led the business and product development activities. He also served as the program manager and eventually the program executive for a mission that I'm very familiar with, the commercially hosted infrared payload, the CHIRP program, which is probably one of the first programs that was on a DoD program on a commercial bus. So that was on an SES spacecraft. He served 22 years in the Air Force in various space operational acquisition and policy positions. And he has a bachelor's degree in electrical engineering from the University of Nebraska, a master's from the University of Colorado, and a master's degree from the Air University. And slightly different twist from the others, he's going to talk about the joint venture between Airbus and OneWeb, and a lot about the automation of their manufacturing process, and how it's going to enable and lead to large constellations under the, the same confines and, of the space network, the communications, the interoperability between the satellites. And so turn it over to Tim.
Thanks. And thanks for the opportunity to be here. I'm glad he didn't say expert again, because that always reminds me of a variable drip under pressure versus somebody who knows something about something. So anyway, so he gave a great introduction on what I'm going to talk about, so we'll just jump right into it. How do you enable low Earth mega constellations? You have to go back and rethink about things, about how you do that. And conversations yesterday from Fred Kennedy during launch and some of the other folks, even on aircraft engines, talking about how do you bring all this together and how do you get away from the ways of developing spacecraft that last 15, 20 years that include human beings. And you kind of have to be able to put some of that aside. So how do you do that? You form a joint venture and kind of tell the guys, follow most of the rules, but you're okay to break some of the rules some of the times, and you have to kind of really set them off. And so that's kind of what we did here. So last year we delivered 24 LEO and GEO spacecraft, as well as the European service module. Glad to be part of the Artemis program. But that's our last year. We plan to deliver double-digit satellite numbers, and it's not because we're going down in numbers, but we're actually going to go to triple digits in 2019. Might be kind of close for MateNet due to some supply chain issues that I won't get too much into, but you can imagine as you're trying to build up and build 648 satellites, sometimes one weak link in the supply chain slows everything down. And we're used to that in the aircraft world, so why not in the space world as well? So it is a joint venture between Airbus and OneWeb, affectionately called OneWeb Satellites, very creative marketing name, but it leads to a little bit of confusion. Good news is we're doing the inauguration of the factory in Florida that'll have 2 final assembly lines on it the 22nd of July. They're already building space hardware, the various sub-assemblies and so forth like that, and we'll start rolling off satellites. And Fred mentioned yesterday, we're on target for a launch of 34 satellites, fourth quarter of this year, hopefully a second launch in fourth quarter also. If not, we start a very aggressive launch campaign of 18 launches in 19 months, all of 32 to 34 satellites, depending on the launch location. How do you get there? You got to go back to, like I said, you got to revolutionize what you're thinking about and your manufacturing capability. We're not building one satellite every 3 years, and it's going to last 15 years. There is room for failure, even though we brought in a lot of reliability. Our number one reliable system, by the way, is the propulsion unit, and for good reasons. One of the things is if other things fell or at the end of mission, since we're at 1,200 kilometers, we want to be able to remove the satellite from the orbit and have it decay naturally. So there's the 90, 97, 98% reliable propulsion system to bring the satellites back down, where the other failure rates can be a little bit higher. But so far, we're 6 for 6 with the 6 we launched in February. They're all at 1,200 kilometers and all operating as planned. So, and we've identified no design changes necessary to address any of the software issues mainly, but that's easily updatable. But so design for manufacturability, you got to look at how you put everything together and what your supply chain can do and work all the way down there. Design for test. You're not going to be testing every one of these. We did 2 qual models. Everything else then is subassembly qualified and assembled. And then what tests do you do of the complete satellite to have confidence that it's going to be successful on orbit? And obviously, when you're launching in a commercial world, you're actually designing for cost. You got to make your business case goes. You got to maintain that, and significant investment in the supply chain to make sure that they're able to deliver on quality, on time, and on cost. And then, look to the future. Don't lock yourself into one design, obviously, because significant investment went into the factory in Florida, and so we have the flexibility there to be able to produce other types of satellites. We're working closely with DARPA right now on their Blackjack program, and part of that is to include an autonomous piece. They want to be able to fly the satellites to fly themselves for 30 to 60 days without any ground contact, to do automatic target recognition, to be able to hand off from one satellite to the next if you're tracking, if you're an electro-optical or a SAR satellite, to be able to go from one to another, and to advance eventually to intersatellite communication links, either RF, but long-term goals, laser, and we're actually bringing that forward. Once again, DARPA's got another payload provider that's on the Blackjack program that's bringing forward some laser communication capability that's light enough for our satellites, doesn't consume all the power we can produce, and is semi-reasonable in cost. So we're getting there. There's some pictures of the factory down in Florida. The chambers there in the center are just day-in-the-life chambers, so we do take the spacecraft once they're fully manufactured, put them in and run them through the thermal cycles. We all know that's kind of the best way to test to see if there is any residual errors in assembly and stuff like that, and then it goes through a final RF test, which is also kind of unique in the fact that we have a test chamber where we put the satellites in there. They're radiated by LED panels to simulate the sunlight, RF hood actually communicating back to the satellite ops center. No cables to unplug when it rolls out, nothing to button up. It is fully tested at that point. And even some of the thermal properties and stuff like that are evaluated to make sure that everything's looking good and the behavior. They're shut off at that time. They're put on the launch rail, and they don't turn on again until they're released from the launch rail on orbit. So there is no testing of the satellites at the launch site. You can't do 18 launches in 19 months if you go down and spend 6 weeks testing them at a launch site. So you had to do, and we're not the first ones to do that. The Iridium satellites did that way back when and stuff like that too. But nonetheless, it's taken advantage of what's been done over the years in doing that. Picture on the right, so what we did there was we didn't do a lot of robotics in the factory. In fact, there's only 2 robots. One's the automatic guided vehicle that runs around at night and moves subassembly from point A to point B. And so the technicians don't have to do that. And then we have 1 robotic arm that helps us put the battery into place because it has to go in above the star sensors and underneath the Ka-band antennas, and we didn't want somebody having a bad day and coming in and bumping something, and then you got to go back and say, how hard was the bump? What do I have to retest? So we do have a robotic assist arm to do that. Otherwise, but the autonomy we put into the software and the assembly system, we have drill guns or the screw guns, know where they are positioned in space, know what step the guy's on, he tags the various parts he's assembling. It sets the torque automatically, it measures the running torque, all that's recorded. And so instead of having, there's no paper, so there's no QA guy coming in initialing off on anything like that. It's all done data-wise. But then we keep all that data, and we can mine that if there's an issue later, either in subsequent ground tests, we can go back and look, or if there's a problem with the spacecraft on orbit, we can go back and do the traceability all the way back through what torque settings were used. Was there a difference? Was the gun running low on power, and we have to change the acceptance values? We do that. So it's going to be a data minefield for just reliability. And then on the satellite ops center, we're pulling telemetry off the satellites once per second. And I mean, the mind can't even imagine, I don't think, what we're going to be able to discover, what we're going to be able to see from the telemetry, from where the satellites are positioned at with the GPS receivers. So they're giving us, meter accuracy on location, how the RF values are changing, all the power levels and all that other stuff. It's going to be interesting to see what we find out from there. I think there's going to be some amazing stuff that we're going to be able to find out once we have 600 plus satellites on orbit. And OneWeb's working on all the autonomy for the software to be able to fly a constellation that could go up to over 2,000 satellites. You got to take man out of the loop. You got to let the machines do what they do. Great fault redundancy capability on the satellites themselves, so they do a lot of fault recovery on their own to keep the mission going without waiting for the next communications with the ground station and so forth like that. So we're building the satellites for OneWeb, and then what's next? So we have the Aero Platform, and that's what we're making available to various other commercial customers, DoD, DARPA, et cetera. What we call the Aero Platform. The one thing I should add on here is lunar communications, because we do think these vehicles will have applicability in that environment as well. So with that, we'll look forward to your questions. Thank you.
Okay, well, we're getting some time signals, so we're going to have a few good questions. Let me see if there are any online first before I go in, and then think about anyone. So I hear there are some online, so let's try that.
Yeah, you bet. So the first question that got outvoted quite a bit was, are encryption or other secure communication concerns a major risk to sharing comms on commercial networks, or are the regulations a larger hurdle?
That was 2 of the questions I had, so really good. Who wants to take that?
Well, I'll start, I guess, if nobody else can. So background when I was in the Air Force, too, was I did some of the space policy stuff, too, as well as helping support CNNSP-12, which is the government standard for encryption and use of encryption devices to include on commercial satellites, so using NSA-approved crypto devices. So, I mean, systems that use encryption, you got to make them compatible, AES-256 and the keys, are very robust. I tell everybody, I said, you don't think twice about using your ATM card or your point of service card or your credit card. It's all about the key management, though. The banks have very secure key management processes, and we're certainly implementing that on our side too, to make sure the key management to keep it secure. But yeah, I've been working for over a year to help get one of the suppliers of an NSA-approved device, their DSP-5, so they can actually so we can send the information overseas to Toulouse, where we've worked with crypto on a national level for a long time. But yeah, getting the regulatory issues to approve some of the stuff is very, very difficult.
But we have been doing it, and we don't see this as an impediment, and we'll be able to use commercial satellite, and we'll provide the kind of encryption needed to protect the transmission. Thank you.
One thing that I like to highlight is encryption, it's a solution, but really we have to look at from the system level how to bring the security in order to be immune, especially when we're talking about the constellation. So one thing that we are looking at APL, it's from really basic hardware component level and bring a security to the space domain.
One of the areas that we've been looking at too is using quantum communications for ultimately secure communication, so using techniques like quantum key distribution.
I think we've got a question in the audience.
Yeah, just a quick thing. Whenever I hear about hundreds of satellites, space debris kind of like bubbles up. And are these satellites that we're discussing, and then not just the Airbus and OneWeb, but are they going to be able to autonomously deorbit in order to prevent the extensive development of more space debris, which, is a really horrible problem?
I will take a stab in that question. So that's a really good question. One reason that why AI in a space domain it's very difficult is because of unpredictability and real time. And I think this problem as a self-driving spacecraft, that it has to be very smart, that intensely look at what are the threats, especially the space debris. And that's the reason that it really takes a long time to have those kind of a self-driving spacecraft. And the debris mitigations, we really have to look at it and start to think about how we can mitigate it, because that will be a very big problem in close future, especially when we're talking about these mega spacecraft constellations.
Yeah, no, and you're right. It's going to be an issue, and I think most of the folks that are manufacturing the constellations have that in the back of their mind. The 25-year rule, insufficient. If you're going to stay up there and decay within 25 years, poor planning. But there's a lot of people launching that do rely on that, and hence one of the, I didn't, because I saw the time card come up, but active debris removal is one of the things, or a tug is one of the things we're looking at being able to do with the Aero Platform. In fact, we built a little hook on the back of it, so even if the propulsion system does fail, we have a much easier chance of going up and capturing it robotically than that. But there's a lot of work going on, and I'm surprised it hasn't made a bigger splash here in the U.S., but the UK Surrey Satellites did some tests a while ago where they actually threw a net out and captured an object to show that they could capture it and bring it back, and then they also showed that they could actually use a harpoon and capture a satellite and then be able to deorbit it.
But as you said, it's a serious problem, and we are not talking about small sat, and these kind of satellite networks. People are looking at CubeSat, and some countries are launching them by the hundreds at once. So we are looking at it right now, studying it, and there are people at NASA that are concerned about it because the human space element, that we need to protect them. We don't want to get one day to, instead of it's raining men, it's raining satellites. So no, it's a serious issue. We are looking at it. Definitely what we've talked about, the cognition and whatever, in an emergency situation when things go out of control, it's going to be a problem.
It looks like we need to wrap up. The next panel is going to be very, very interesting with Back to the Moon. So thank you to all the panelists. This has been fun getting ready for it, and look forward to talking to you guys some more. Thank you.